All right. I'm going to be talking about this feature that we call dynamic PGO. It's in .NET 8. There were some preliminary versions of it that you could opt into in .NET 6 and .NET 7, but in .NET 8, it's now the default behavior of the runtime. I'd hoped to be co-presenting along with Egor Bogatov, who also did a lot of good work on this feature. Fortunately, Egor couldn't make it, so I'm going to do my best to cover his content as well as mine. So you probably have heard in some of the other sessions that .NET 8 is fast, that there are a lot of compelling performance improvements that have been made all up and down the stack. Of course, we said that when .NET 7 came out, that it brought compelling performance improvements over .NET 6, which brought compelling performance improvements over .NET 5. So you might get the idea that we've got a pretty good cadence here of making .NET performance better and better and better with each release. And the way we do that, it's pretty simple. We make thousands of improvements every time, all across the product, big and small. If you're a fan of this stuff, you can read Steve Tube's blog that goes into it in a lot more detail. Let's see if I can fix the light here. It's a little weird. Hold on a sec. And I'm in the shadow here. If you read that, his blog, it's quite long. It goes over all sorts of features that are better. One of the big ones, and one of the ones that he's liked the feature and that we're excited about, is dynamic PGO. And so what does dynamic PGO do? Basically, behind the scenes, without you having to do anything whatsoever, it will boost the performance of your application. 15% is typical. It's very difficult to boil things down actually to one number, so I'm a little hesitant to say I can guarantee you're going to see 15%. Some things will see more, some things may see less. But here's a sampling of things that people have seen when they've turned it on. The one on the bottom there was from .NET 7, but the feature was pretty similar at that point. So Akka saw some very nice speed ups. And then you can see some other people who've turned it on. And if you look at the upper right there, you can see between 6, 7, and 8, there's been just a steady improvement in this particular application, and a bunch of other examples as well. So we think that when you deploy this in your system, you hopefully will see similar benefits. And in this talk, I'm going to tell you a little bit more about how all of this stuff happens. Now, it's really all behind the scenes. As I say, you don't really need to do anything to get it other than to move your application to .NET 8. And if you have already opted into PGO in earlier releases, we'll tell you what to do in .NET 8. If for some reason you need to turn it off, we'll tell you how to do that. And then some things to think about, especially if you do a lot of benchmarking. PGO and benchmarking interact. We generally have, I think, the interactions in a good place, but there are some gotchas to watch for. So what is it that PGO is? Well, it's an acronym. It's an initialism that stands for Profile Guided Optimization. And really here, the idea is that we sort of give hints to the compiler, in this case, the .NET JIT, as to how to better optimize your code. In particular, we try to look at what your application actually does and focus the optimizations of the JIT on those specific behaviors of your optimization. Now, the thing that's different here with dynamic PGO is that you don't need to do anything to enable this optimization flow. What happens is that entirely in the process, as your application is running, the runtime and the JIT are conspiring together to sort of monitor what your application is doing and direct the JIT to go and produce better code for the methods in your application that matter the most for performance. And so you may have heard of similar things in other technology stacks, like in Java, you might have heard of Hotspot and trace JITs in JavaScript. These are the same kinds of ideas where we're using real-time feedback as the application runs in order to go figure out better ways to make the application run even faster. And so let's talk about some of the key optimizations that we turn on when PGO is active. The main one that we like to talk about is something called guarded devirtualization. That's kind of a mouthful, but there's basically two key things here. One is that we are able to look through various kinds of constructs that are pretty common in most programs, those being virtual and interface and now even delegate calls, and figure out what methods are actually being invoked, at least most of the time. We have a pretty good idea, like, hey, this is actually your IEnumerable of T is actually a list, and so we know that when you enumerate through it, you're actually enumerating through a list, and we can special case your code for those sorts of things. And so the way that we sort of describe this in the optimization literature is we say that your virtual and interface calls are monomorphic. There's just one thing that actually happens at one time, or one common thing that happens at runtime, even though the code itself has the potential to have many different things happen. And so what we do in these cases is we observe the behavior of your application. We see that at this call site, you are always invoking the same interface method on the same class. And then we recompile the code and we add a test for that specific case, which we call a guard. If we see that that guard is successful, we know exactly what kind of data type you're operating on. We optimize for that case, typically by enabling inlining and other things that follow through from that. We do a good job if you happen to be doing things on boxed instances, for example. If it turns out that we were wrong, that the data is actually different than we thought, we just do the normal behavior that you get now. And so this is the whole notion of doing a little bit where we try to guess what your program is going to do based upon some good information, what we saw your program doing just recently. If we're right, we can see some really nice performance benefits. So here's an example that sort of makes it a little more concrete. We have some sort of interface, iUser service. We have a method that basically takes that service as a parameter, and it basically just makes a call through it, right? And so normally you would expect that when we go to JIT this code, we would have no idea what method actually gets invoked because it would depend upon the actual type of the service object that gets passed in. Now what we do first then is the first time we JIT this method, we like, all right, let's see if we can get some idea if the same kind of type comes in here every time. And so we add a profile call behind the scenes. You don't have to do anything with this. It just happens automatically. We look at the type of the thing that you pass in, and we effectively build like a little histogram for it. And we keep that stuff all in the memory of the process somewhere. And we let this version run for a while, and we see what sort of types get collected up on our histogram. And then once we have enough data, we flip around and we re-optimize the method. Now we say, aha, we notice when you call this thing, you're always passing in a user service impl for your service. So let's check for exactly that case. And that, if test there basically saying, is this the class that we sort of commonly see? If so, then we can directly call the right method on that object. If not, we go back and we do the general interface call. So this is the idea of the guarded devirtualization. The if is the guard. The devirtualization is the fact that now we're directly calling the right method if our guarding is right. Now, once you do that, then you can start to do even more things to optimize further. For example, if this call happened to be in a loop, it turns out that you're looping over, say, and this is very common with enumeration, you're looping over the same object and you're calling methods on it over and over and over again. We can invert the order of these things and we can do the test outside of the loop and then create two versions of the loop, one of where we're right and we know what kind of object we're dealing with, and one of where we're not sure. And if we're right, then that loop becomes extremely efficient. And the thing we go after here is this concept, you may have heard it called de-abstraction or zero-cost abstraction, which is you write your code in a very general way, but when you run it, it doesn't have very general behavior. It has very specific behavior. We recognize that specific behavior. We optimize for it. And so you get the benefit of programming in a very abstract, general, high-level way. We get the benefit of optimizing it if you'd written exactly, for loop over an array or something equivalent to that. So this is still a work in progress, but we've made pretty good stuff on it. So things like link actually get fairly dramatically faster because we understand, hey, you're not doing anything crazy like passing in many, many different kinds of data into your link thing. Your underlying data is actually something very predictable. We take advantage of that. And so here's an example of how all of that would play out. Let's imagine that we have a loop, and the loop is walking over, in this case, just 10,000 integers. And inside of there, we're going to call some delegate, and we're going to sum up the results of calling a delegate on each of these integers. So what we would do in our initial compilation, the thing that we call tier 0, is we would add a probe into the code to say, wait a minute, let's see what kind of delegate we have each time here. And when we get down to re-optimizing, we'd say, aha, we know that we only ever see this one delegate come in here very commonly. Let's check for that specific case and optimize it. And then because we know exactly what's being invoked, we can inline it. So let's say what all of this delegate does is say increment turn value of i+1. So we can suddenly get rid of all of the calls on that one path. We do one check. When we get the check done, we go into the loop and we just add. So So you can imagine this ends up being much, much faster than invoking the delegate every time along. So we're actually saving a lot of loop. And you'll notice that the guard here, even though the call was inside the loop, the guard here is outside the loop. So there's an example where we've done this kind of hosting and cloning to try to take advantage of the fact that this fact that we learn is true for many, many, many loop iterations. So another key optimization that the JIT will do is inlining. And we use the data that we gather when we are doing our instrumentation to actually tell the inliner about which inlinees are the key ones to inline for a method. And because of that, we can actually make the inliner be much more aggressive and inline maybe bigger and more ambitiously than we would if we didn't have profile data. And then if we see parts of the method are less important, then we can sort of back off and do less inlining. So on a whole, we spend about the same amount of time jitting, but we've focused our effort on the parts of the method that really make a difference for performance. Here's one example that shows how ambitious we can be. There's actually a method that comes from the BCL. It just asks if a type is a primitive type. And okay, the method may look not that complicated. It's just kind of doing the same thing over and over again with different types. When you actually look at how that method gets compiled into intermediate code, it turns out that all of these operations turn into method calls. So I don't know if you can all parse IL code here over on the right, but you can see that we basically get a description, say that first line of the Boolean type, and then we convert it into this special object, and then we call to see whether that, to get the actual runtime type object that represents Boolean. Then we convert that and we call it an equality method. And if that's true, we branch. But it turns out that even though this thing is conceptually simple, it actually generates a fairly big method body. In this case, I forget, 271 bytes of IL. Now, normally the JIT is extremely cautious about inlining methods that are this big because typically they aren't going to pay off. But because we have profile data, we can sort of peer in here and we can see, aha, wait a minute. We happen to know, for example, in this example, we only call it with, say, int or float. We sort of collect up that data and we're like, we see that most of the time, most of those checks in there are going to be false and we don't need to even bother making them. We can just sort of skip them. And so we go ahead and we optimize this thing. And it turns out in that case, when you optimize it and you are able to inline it and propagate those types in there, all of these things fold down to either true or false. And we know how to combine a whole bunch of trues and falses that are connected by ORs into a constant. And so the result of this, I don't know how many of you read x64 assembly languages, effectively just return true from that installation. So we've boiled down this 271 bytes of IL in a method that you call a lot to basically doing extremely little work. We basically set the result to 1 and we return. So a lot of things happen if we sort of know where to focus our effort. We knew that this method mattered. We knew that it was worth doing this extra analysis to try to decide that this was a good thing to inline. We did the inline and we got it, and then we got a great result. Another thing that we do fairly aggressively is we rearrange the order in which we generate the code for your method in order to take advantage of profiles. And the idea here, if you're familiar with the idea of locality of references, we want to try to compact all the important code that we generated your method into sort of a small area and leave the less important code somewhere else so that the instruction cache in the processor is mostly occupied with instructions that are in the parts of your method that matter. So again, here, that sort of example that we showed before with a delegate, we know that this code in the orange is like the most important code in the method. This is the loop where we knew the right kind of delegate, we inlined it, we know what it's going to do. We try to keep that very close to the front of the method, and then the remainder of the stuff happens, and it happens elsewhere. So that orange stuff is the actual loop, and then the blue stuff is the guard. Remember, this is a guarded devirtualization kind of thing. The stuff right above that is just kind of boilerplate to come into the method. This is what we call the prologue, and that's pretty much it. We go into the prologue, we figure out if we're in the case that we think is optimal. If so, we have the compact code right at the front of the method for generating it, and then we're done. So you get some nice benefits out of this as far as if your method has a lot of code in it, we now are starting to make better use of it. The instruction caches on the machine to make sure to accelerate performance of your application. So let me talk a little bit about how we actually gather the data that we use to optimize. The first key thing to understand is that in .NET now, methods are JITted multiple times, and we call this tiered compilation. We've had this feature for quite a while. And so the flow chart over there on the right is trying to give you a rough picture of what might happen. If we see that there's some method in your code that needs to be called, the first thing we'll check is, well, did you happen to pre-JIT the method? That's an option that you have using ready to run. If so, that's great. We can just sort of use that version directly. We don't have to JIT it. But if you start using that ready to run code a lot, so now we're on the right branch of the flowchart, we see that you're calling that ready to run method. We'd be like, well, it turns out the ready to run method isn't as optimized as it could be because we had to produce that ahead of time. We didn't know how your application was going to use this method. We didn't have a chance to optimize it specifically for what you're doing. So we end up rejitting it, and this time we add in instrumentation to this ready to run method. And this is a new feature in .NET 8. We didn't used to be able to do this, so this is a new thing. We watch that instrumented version run for a while. We see what it does, and then we optimize it again, this time removing the instrumentation and using the results of the instrumentation to drive optimizations like we showed. And so this gives us the ability, even if you pre-JITted your method, to go in and get another look at it and potentially redo the code for it and produce better code that actually is then run. The method wasn't pre-JITted, now we're on the left branch. We first do a very quick compilation to try to get your application running and get some code that you can use. If that gets called a lot, we redo that method and we instrument it. If that gets called a lot, we redo it and now we optimize it using the profile data. So either way, no matter whether you pre-JITted your methods or not, you end up with a version that was instrumented that gathers data, a version that's optimized that reacts to that data. The actual picture is a little more complicated. We left off some interesting things. If you're curious, there's a lot of documentation on the .NET Runtime site that talks about exactly how all this plays together. But that gives you the gist of it, that we're very thoughtful about trying to make sure every method that runs, we have a chance to observe and then optimize. And this is the new capability that we just referred to for optimizing instrumented optimized code. So this version that we show here on the right, this is the unoptimized code. And the only thing you'll notice about it, excuse me, is that there's potentially a lot of instructions in there. If we do the instrumented and optimized version, you can see that part of optimization is to actually use the machine more effectively. We now generate far fewer instructions, right? We still have that class profile 32 in there, which is the thing that we use to probe what types are involved. And so we're actually looking at the types, excuse me, building up the histogram. I probably don't parse this, but the call there is a general interface call. And then once we're done with that, we go ahead and we optimize it, and we end up with the kind of code that we showed before. Another thing that we've done in .NET 8 is we've put a lot of attention in trying to reduce the cost of instrumentation. Now, instrumentation isn't free. We're in there measuring things that we weren't measuring before. We try to be really, really thoughtful about having that instrumentation have as little impact as possible. And a couple of the things that we did, I'll just highlight them. We now do what's called sparse edge profiling. So instead of counting every single basic block in your program and figuring out how often the different parts execute, we now try to be clever, and we use something called the depth first spanning tree to place things sparsely throughout the method and then reconstruct the counts from that. We moved a bunch of things that are involved in all of this into what's called thread local storage, so that if you have multiple threads running, they don't interfere with one another. We did some work to reduce the impact of the profile counters when you do have multiple threads by things like false sharing, by trying to reduce the number of updates, excuse me, by doing some probabilistic counting. And then there's some cases where the JIT doesn't bother to instrument the method because there's nothing to be learned. Like if your method just, say, returns 3, we're not going to learn anything by instrumenting that method. It's just going to return 3, so we don't do it. Those examples are the kind of things we put to try to keep the instrumentation cost low. There's an example of the payoff of that. If you look up here, that this is on the left is a performance chart where higher is better. So a normal optimized code is up there with the black line. If we force the application to stay in tier 0 and we don't allow it to re-optimize any methods, you can see the performance drops by about a factor of 2. If we then also put instrumentation into that code, well, for a long time, the results were not very good. And you can see this is over time. So something happened there in April of 2023 that made it dramatically better, which was the introduction of this sparse counting technique that I just talked about. And now the instrumentation overhead is actually pretty close to having no instrumentation. And the picture on the right is latency, and it shows likewise the latency was pretty bad when we had instrumentation in, and it's now dropped dramatically, and there's really no impact that way either. All right, so let's quickly switch gears here. What do you have to do to enable dynamic PGO for your application? Very simple. You update to .NET 8. Nothing else. That's all you have to do. Now, if you had been using PGO previously, you want to make sure that you are not, or you had done some unusual configuration in your runtime. You may want to make sure you're not disabling some of the things that all of this depends upon. So you want to leave tiered compilation alone. You want to leave ready to run alone. You want to leave quick chip for loops alone. You want to leave on stack replacement alone. You don't know what any of these are. You don't need to. They're things that you might have set in the past for various reasons, but you should consider unsetting them now if you are setting them. And exactly, I think this is basically saying the same thing. You can remove these settings if you had them. They are no longer needed. We've sort of fixed all of the issues that made it necessary to sort of alter the behavior of the runtime when you opted into PGO in the past. So none of this is needed anymore. Now, if you end up having to disable PGO for some reason, you can either do it with an environment variable, or you can do it with a project setting, or you can do it in the runtime config. That will basically put the runtime back to the way that it behaved in .NET 7. If you end up doing this for whatever reason, please let us know so we can figure out what led you to do this and how we can make things better. You can open an issue with us on GitHub or get a hold of us anyway that makes sense to you, because we really do want to see cases where it doesn't meet your expectations and we can do better. A little bit about performance and benchmarking. So we turned on PGO on May 19th in our repo. And so you can see like this benchmark chart here, sort of in the middle left. Suddenly performance of this thing dramatically improved. This is some iteration over an immutable sorted dictionary, but a lot of these more complicated data types showed some dramatic improvements. We've also been using some of our internal first-party customers as early adopters. So Active Directory Gateway picked up PGO back in .NET 6 and saw some nice benefits. And other people here and there have used it for various things. So we've seen a lot of good things in our own benchmark system there. You see, when we turned it on, there were over 1,200 benchmarks that improved from dynamic PGO. So when you turn PGO on, or when you pick up .NET 8 and you find PGO is on by default, you should see an improvement in performance. If your application is extremely short running, like the matter of a couple seconds, and it's JIT intensive, you may not see improvements. And if it turns out that you don't see improvements and you decide because of that you have to turn off PGO, you may still see benefits from .NET 8 from all the other work that people have done all up and down the stack. So we would be sad if you turned it off, but .NET 8 is still going to give you benefits anyways. You may see a little bit of impact to startup, either a slightly longer startup time, or if you're on a server and you're measuring latency right at startup, you may see somewhat increased latency. You will see more methods JITted overall if you're looking at that sort of thing, because now methods can be JITted multiple times. And there's always a chance that there's an issue that's specific to PGO, either a problem with the correctness or performance. If you suspect you have one of those and you disable things via PGO and by turning off PGO and things get better, again, please let us know so we can get the issue fixed. For benchmarking, just real quickly, there's one thing that I want to keep an eye on, and that is that the PGO system is really good at watching what you're doing. So if your benchmark is too simplistic, if your input data set for your benchmark doesn't represent the thing that you actually care about, you may get misleading results. So for example, passing a constant string into a benchmark method, we may know exactly what string it's operating on and optimize the code for that specific string. So you want to make sure that when you're benchmarking, you put in a realistic mix of data that represents the kind of thing that you care about. This chart is supposed to show you that if I pass in only class A to this benchmark, I get one level of performance. And if I pass in only class B, I get the same level of performance. But if I pass in a mixture of half A and half B, the performance is actually much worse than if I have an unmixed thing. So in this particular case, it goes from about 2.5 nanoseconds to 8 nanoseconds. This was before PGO was enabled. With PGO, it actually goes from about 0 to about 2. So the impact is still there. It's just something to watch for when you're benchmarking. Try to benchmark as realistic a thing as you possibly can. And then finally, this also plays okay with native AOT. We don't have a PGO story right now for native AOT, but many of these same optimizations will kick in for you automatically because native AOT has what we call a closed world assumption. So even though we don't know specifically what types your application is using, we know the set of types is limited because of the way native AOT works. And so sometimes we take advantage of that to do similar kinds of optimizations. Anyways, to recap, Dynamic PGO is now enabled by default in .NET 8. It offers a broad range of performance improvements. Sometimes people say the more complicated your app is, the better it is. I mean, it isn't phased by the most complicated applications out there. All you need to do to turn it on is just update to .NET 8, and please let us know what you think about it, either good or bad. And here's where you can get .NET 8 if you're not sure by now. And then also, we generally like to get feedback and stuff on the .NET 8 runtime repo. So feel free to open issues there, leave notes, get a hold of us there. We're happy to, look at all feedback, both good and bad. And that's what I got. So thank you very much.
Oh, Andy, what can I say? Knowing that just upgrading, you're going to get PGO turned on in .NET 8, dynamic PGO, and it's going to just improve your application. That's right. That's one of the nuggets that you get when you use a framework like .NET.
Yeah.
It's always improving.
We always try to make it better all the time. And as you've seen in the past, I think we've had a pretty solid track record of making things better one release over the next. Yeah, this is just sort of the next step, the next evolution. But it's one that we're particularly excited about. So.
Oh, definitely. Now, there was a question that I want to make sure that we go to from Samuel on YouTube.
Sure.
And there it is right there. We've been doing a lot with ARM recently. Does PGO also work on ARM processors?
Yeah, absolutely. It works on all the platforms that we support, and though it works on x86 if you're on x86 still, it works on x64 whether you're on Intel or you're on Windows or you're on old style Mac OS, and it works on ARM whether you're on Intel, Windows, or Mac as well. So yeah, it's pretty much all the same.
Awesome stuff. Thank you so much, Andy.
Sure.
Really appreciate you going deep and showing us the nuts and bolts of how this all fits together.
Yeah, I mean, I wish I could go deeper, but I know we only got so much time. So this sort of gives you the highlights. Should be, I think, a no-brainer to just pick it up and see what it does, and hopefully everybody sees really good stuff.
Absolutely. So, you take care. Thank you so much for joining us with .NET Conf this year.
Yeah, happy to be here.